Hello, everyone, and welcome to this edition of the tutorials by SkillForge. I'm Suelanji Trachala, and what I want is to actually give you an understanding in data structures and algorithms, particularly when we talk about algorithms. Okay, so as mentioned in my group chat, I have said that I'm going to be a little bit occupied this coming month, so there are going to be videos that are just going to be there, and I'm just going to be uploading them as the days for the tutorials are there. So at least you have something to work with. Okay, so without further ado, let me just share my screen there so that we see how best we can start doing what we need to do here. All right, cool. So let us begin our tutorial session if we can get that started. Okay, cool. So today we're talking about data structures and algorithms. And particularly, we're talking about algorithms in complexity. Let me just, what's that? Okay. Okay, so we're talking about algorithm complexity, and we're analyzing time complexity of algorithms. So how do you solve these types of questions? So particularly what you do is that you need to understand, just move this is distracting. Okay, so you first need to understand big O notation, right? So by understanding what big O notation is, you better understand how to solve algorithms or find the time complexity of algorithms. And again, you can just text in the message area, in the comments area, then I'll respond to your text, or you can just send in a group chat and then I'll respond to your text when I'm available. Okay, so understanding the big O notation. Let me just get my screen there. My highlighter, just choose a red pen. So big O notation is a mathematical notation used to describe the efficiency of an algorithm in terms of time and space complexity as input size grows. So what this means is basically we're using mathematical notations to understand how algorithms work, right? How fast algorithms expand, and also how everything goes, right? So with that, we can say that big O notation just helps us understand how much time an algorithm is going to take to execute, or how much space it accumulates as it's running its program. I hope that makes sense. So big O notation describes the worst case performance, right? So there is small o and also big O, and small o just gets the best case scenario, whereas big O chooses the worst case scenario, so that we better prepare for ourselves, right? So it's kind of like the extreme of the worst. So we're just saying the worst case scenario is this. So meaning if we can account for this situation, then all that's left is just the best case scenario, and then we're good, right? So big O notation describes the worst case scenario, and it indicates the upper bound on execution time and space usage. So big O also ignores constants and lower order terms, so meaning that it focuses on the dominant factor that is affecting growth. So basically, if we're saying that we've got a higher order function that is, let's just say, I hope I can do this. Let's just say we have big O of a function that is, let's just say, n squared, right? And then we've got big O. Exponentially, we know that if n is 1, or so if n is 2, then n squared is going to be 4, right? So the bigger between the two is going to be n squared. So meaning our algorithm is going to dwell on this particular concept here. This is the higher order terms. So it's going to ignore this function here, and then it's just going to focus on our guy there. I hope it makes sense. Okay. So the common use cases for big O notation is that it's used to compare and optimize algorithms in competitive programming and software development. So in the sense of whereby you need to understand or analyze how best the program is going to execute in planning and whatever, you're going to need to know the space and time complexity of these particular algorithms. If you want to create a Python program that does a particular function, but then it requires a lot of, let's just say, loops, it's going to take a lot of time, and it's going to take a lot of space, it's going to take a lot of memory, so you have to account for that as well. Okay, so time complexity and space complexity in a general sense is that time complexity refers to the amount of time the algorithm takes to run as a function of the input size, right? So factors that affect time complexity could be number of iterations in loops. So loops is a factor here, right? The recursive calls. This is also, let's just say, when a loop calls upon itself or a function that calls upon itself, we can have an n-log type of time complexity, and operations performed on data structures, meaning insertion, deletion, searching, etc. Yeah, so basically that's how that's what time complexity is. Essentially, in a nutshell, it refers to the amount of time an algorithm takes to run as a function of the input size, n here, as we can see. And I miss having the live sessions, because at this point I could ask you if there are any questions so far and whatnot, but yeah, we just have to work with what we have. Okay, so space complexity refers to the amount of memory an algorithm needs to execute based on its input size, which is n there. So types of space requirements are fixed parts, which are independent of the input size, that is variables, constants, or whatnot, that takes a lot of space. So remember, in programming languages and paradigms, you know that variables, when we declare them, they are allocated in a specific space in memory, right? So space complexity actually just focuses on the amount of memory an algorithm needs to execute based off the input size. So if we get a variable, let's just say a variable int var, right? How big is int var? Or we assign a variable to a loop. How big is that loop going to be, and whatnot? So that's fixed part. And then variable part depends on input size, e.g., dynamic memory allocation and recursion stack, etc., etc. So we have those types of outputs and everything. So we can just see the type of complexity that we have in space complexity there. So here is a little bit of a, just move this. Here is a little bit of a hierarchy of complexity classes, starting from the lowest to the highest here. So here we have big O of 1, which is our constant, usually C. Let me just do this. So this is usually denoted as C, and we see that it has the lowest execution time, let's just say, right? Of all of them here, this big O of 1 is the lowest execution time. Then big O of log n is the second slowest, right? Or let's just say if we're looking at from slowest to fastest, we have this type of arrangement here, where here we have slow, quick. Let's say quick here. Where is this guy? Let me just give him an eraser. Okay. So here we say quick execution time, Q. Let me just say Q here. So Q for quick, and then here we've got slow. Yeah. So we've got quick execution time, which is big O of 1. And this might be a little bit confusing, but big O of 1 is the fastest to execute. Remember when we talked about big O, we look at the order or the higher order functions or the higher order operations, right? So which one is bigger and which one is smaller? So big O of 1, which is a constant, is smaller because it has less time to execute and it also has less memory to keep, right? And the second fastest is big O of log n, right? So that one has got an execution time from here to here, which is faster than our big O of 1. And then we have big O of n, which is slightly slower but larger than big O of log n. And then here we have n log n, which is bigger, greater than big O of n, and then here we have big O of n squared. Okay, so big O of n squared is bigger than n log n, and then big O of 2 to the power n, right? So this is big O of n squared, and then this one is 2 to the power n. So both of them are exponential, but then this one has got a greater yield. It's going to be slower because it's larger. It takes a lot of space. It takes a lot of time as well. So here the space complexity and the time complexity, is going to be big O of n squared, which is quite faster than big O of 2 to the power n, right? And then the slowest of them all, and the one that requires the most space and time complexity, is big O of n factorial. Okay, so just try to understand this. This is the order, this is the hierarchy. So the fastest is big O of 1, which is a constant, and the slowest is big O of n factorial. So we have that. So the hierarchy of complexity classes from base to worst cases. We've got constant time. I've already explained this, but let me just run through it. So execution time remains constant regardless of the input size. So an example could be accessing an array in an element array. So we've got an array, let's just say we've got A there, right? And then we've got an array, sorry for that, array at I. Huh? Okay, sorry about that. Yeah, sorry about that. We had a little something. Anyway, so where was I? So constant time there. So basically, if you want to access an element in an array, right? Let's just say an array at point I, that has got a constant time because it's got a fixed space in our memory, and the fact that it has a fixed space in our memory, meaning that it's easily accessible to the program, right? So it's got a fast memory allocation, it's got whatnot and everything. So yeah. So second is logarithmic time, where the execution time increases logarithmically with input size. So an example could be a binary search algorithm. That's going to be discussed later on, but yeah, we have that. Then big O of n, which is linear time, and execution time increases proportionally with input size. So example, maybe traversing the array, right? So the difference between accessing the array, an element in an array, and traversing the array, there's a difference between the size. So for example, we can say a function could be for, let me just say, for 1 to, let's just say, 5. So let me just erase that. Okay. So for 1 to 5, right? So traversing this array from 1 to 5, that takes the big O of n linear time. Okay, but then if you're just accessing that particular element, meaning we're just going to say that A1 is going to be equal to, let's just say, sum, right? Just put that there. Okay, so A1 is equal to sum. This has got a constant time because we're accessing an element in an array, which is different from traversing an array. Okay, so we can have this for 1 to 5, and then we've got an array at I and whatnot. Let me just put this for I there. Yeah, so for I, 1 to 5 and whatnot and everything. So traversing an array takes big O of n linear time compared to accessing an element in an array. Okay, so don't get the two mixed up. All right, so big O of n log n, which is linear rhythmic time. Execution time is the combination of linear and logarithmic growth. So these two combined gives us linear rhythmic time and is efficient for sorting algorithms like merge sort, quick sort, and all this other stuff. So by that count, it's faster. Also, it's not faster, it's a bit slower than linear time. And it gets a lot more memory because it's growing, right? So as it grows, it allocates more memory, and then yeah, so we need for that. Then there's big O of n squared, which is quadratic time. Then execution time increases quadratically with input size. So nested loops in bubble sort and selection sort. So that's self-explanatory. Then exponential time, meaning execution time doubles with each increase in input size. So this is exponential actually. So this is quadratic, this is exponential. I think I made a mistake just mixing up the two. So an example could be recursive algorithms like the naive Fibonacci sequence computation. And finally, we've got the big O of n factorial, which execution time grows factorially with input size. So solving the traversing salesman problem with brute force. Okay, so there's that. So here's a chart and the summary of growth that basically just sums up with everything, right? So we have the best here, which is big O of 1, which is our constant time, log n, then big O of n, then big O of n log n. So this guy is the middle guy, right? So they're about 1, 2, 3, 4, 5, 6, 7. So this on point number 4, we see that this guy is in the center of everything. And yeah, basically this one is in the middle. If you're looking at order of operations or hierarchy, just remember that n log n is in the center. Then we have big O of 1 at the best side, and then on the worst side we've got big O of n factorial. Then we have the worst case scenarios, which is big O of n squared, which is quadratic, and then this guy is factorial, then this guy is this. So the highest and the worst case in terms of memory is the big O of n factorial, and then the lowest and the fastest is big O of 1, which is constant time. And then we see here, so examples of all these guys. So you can just maybe try to take a screenshot, or maybe you can come back for this later. Okay, so now let's try to actually now solve complexity, right? So first things first, we have some rules to follow. Okay, so rule number 1 is that if the time complexity of our factor n, or our algorithm n, is equal to big O of our function f of n, and also t2 is equals to n, and then we've got g function. So let's just say we have a function, let's just say big O of, let's just say time complexity is, or time complexity of 1 is, let's just say big O of n, right? And then t2 is, let me just do that, big O of n squared, right? So if t1 is equal to big O of n and t2 is equal to big O of n squared, then the addition between these two here is going to be equal to t1. So the addition between these two here, what this function here is saying that t1 m plus t2 n is equal to big O of fm plus gn. And then here it also says that intuitively and less formally, it is big O, the maximum between these two functions. So we're saying that when we add these two time complexities, the overall big O function is going to be the highest order. Remember, when we started, we said that big O looks at the worst case scenario, and here we're looking at the worst case scenario in the sense that this guy is the one that is the largest one compared to this guy here. So if we add the time complexity of algorithm 1 and also time complexity of algorithm 2, then our overall function is going to be big O of the maximum value between, just put mx there for max, maximum value between big O of n, just put that there, big O of n plus big O, oh, sorry, not plus, sorry, not plus, but comma, big O of n squared. Okay, so this might look like it's a lot of gibberish and whatnot and everything like that there. And yeah, it's kind of, confusing. But then this essentially means that if you've got a function here, right, the time complexity of this function is equal to that, and the time complexity of this function is equal to that. So when you add the time complexity of algorithm A and add the time complexity of algorithm B, which is this guy here, what essentially we are doing is we're saying that we get the biggest of them all, and that's going to be our overall time complexity. Meaning that when we add algorithm A and algorithm B here, we are saying that we get the maximum between these two algorithms. So the maximum of these two algorithms, T1 and T2, is basically big O of n squared. That's what we're saying for this rule. So rule number one says that if we've got, I'll repeat it again. If we have Tn, we've got our time complexity of algorithm 1 and also time complexity of algorithm 2. We have that there, right? When we add these two time complexities here, what we're getting is the maximum of the two complexities. I hope that makes sense. Okay. Then here, when we are multiplying these guys here, we're just saying that. Let me just do this here so that I can save space. So what we're saying is that if we multiply these two functions here, then the time complexity is going to be, let me get my eraser here. My complexity is there. Okay, so when we multiply these two algorithms, our time complexity is going to be big O, right? Here we're saying big O of the function there, which is going to be n, which is this n there, multiplied by n squared. Okay, and the rule of indices says that here we have n to the power 1 multiplied by n to the power 2, and we are multiplying with the same base but different powers. We add the powers there. So our final answer here is going to be, let's do that there. Our final answer here is going to be n to the power 3, like that. So here when we have a time complexity of this guy and then also time complexity of this guy, when you multiply these two functions, we multiply the big O of those two, which is big O of n to the power 1, which is this guy here, big O to n to the power 2, which is that guy there. So when you multiply these two, we have big O of n to the power 3, like that. Okay, so that's rule number 1. I hope that's clear. So rule number 2 says that if the time complexity is a polynomial of the degree k, right, then the time complexity is going to be equal to t to the power of k, right? Rule 3 is, so this one is basically just the same as this guy. So if Tn is a polynomial of the degree k, then the time complexity is of that polynomial. It's the same thing as this guy here. So it's the same as rule 1b, same thing. So you just multiply it by the time complexity there. Okay, so rule 3 says that log k of n is equal to 0 for any constant which is k. So k is a constant value, right? This tells us that logarithms grow very slowly. So this is just some technical understanding, but theoretically speaking or solving, you only need to know these guys here, these two, rule number 1. Rule number 2 and rule number 3 is just for formality's sake. All right. So with that being said, let me just show you a bit on how to answer these questions. Okay, so again, I wish there was a point whereby we could discuss and you guys actually like making this session interactive, let's just say. But because of circumstances, we can have this. So yeah. So remember, we talked about something about a constant time, right? Meaning something that's allocated in memory. So we see that sum is equal to 0 there, right? Here we are assigning something into memory. Okay, so this assignment operation has got a constant time. So always remember some key factors here, some keys. Let me just put that there. Keys. So if it is assignment, oh my goodness, okay. Okay, so if it is assignment, then it is a constant time of, so it's got a time complexity of C. Assignment meaning that it's got a 0. So if you say sum is equal to 0, that's anything that is assigning something. So sum is equal to 0 has got a constant time. I is equal to 0 has got a constant time here, right? Yeah. So anything that is assigning something, meaning if it's got an equal sign, then it means that it's constant time. Okay. But if it's got an n, we don't know what n is. So if it has something like n, j, these are the way they are. So you've got n like that, right? So c and then I plus plus, these are just incrementing. So remember in your programming, what's this? So in your assignment there, I plus plus is equivalent to I plus 1, right? So I plus plus is equivalent to I plus 1 if you're looking at your incremental operators. So what that means basically is that when we have I plus plus here, we are assigning it to say this I is equal to I plus 1. Okay, it's almost the same thing if you're trying to understand it in a technical format. This I plus plus is the same as I plus 1. So there is that type of iteration there. So hoping that we've understood this concept, we can now try to solve this. So remember, if it's n or j, then it means that has got an n value there. If it is multiplication like this, then we just multiply based off the rules that we had already. Okay, so let's get into solving this actually. Okay, I wish I had a touchpad, but yeah, let's have what we have. Okay, so let's begin solving this. All right, this one is very easy. So sum is equal to 0, right? And remember, assignment operation has got a constant time. Assignment operation has got a constant time. So here we put that as C. Then what we're going to do next is we're going to say for I is equal to 0, which is also going to be a constant time there, comma, I is less than n. So here we've got time complexity of n. Okay. Oh, another thing is that if it's n, we count it as n. But then if it's 8, for example, let's just say 8, 7, 6, or whatnot, then it means that it's got constant time as well. So if you had something like for I is equal to 0, I is less than 8, I plus plus, the time complexity of this algorithm would be constant, meaning big O of 1. Okay, so that's just something to look forward to. Okay, so for I is equal to 0, constant time. For I is less than n, it's got a time complexity of n, and then I plus plus is C there. So remember, the plus plus here has got an equal to sign there. So sum is equated to some space in memory, so this is also constant time. Adding all this together, we have big O of C plus C plus N. So C, which is this C here, C, which is that C there, N, which is that N, then C, this guy here, then plus the final C, which is here, like that. And remember, in rule number 1A, right, we said that here, if we have these functions, what we do is that we collect the highest order. And we saw from the graph there that the highest order is N there. So the time complexity of this algorithm is big O of N. Simple enough, right? So big O of N. Okay, cool. So from that understanding, let's also try to solve this guy here. This one is a little bit tricky, so we'll try to understand what we can. So for nested loops, always remember that we are multiplying them. So there's a multiplication sign here for nested loops. Okay, don't forget, nested loops are multiplying by themselves, but then for assignment operations and all that, we add. Okay, so we have big O of C there, constant time. Then here we have constant time as well. We have N as well there. I've got constant time. And then here we've got J, which is constant time as well. And then we've got N as well here, because J is assigned there, and then we're equating into less than N. And then here we've got constant time as well. Then we've got C. So grouping this would be that for the first O of C, let me just do that there. Okay, big O of C. Here, by this logic here, we already understand there 0 or big O, which is going to be the time complexity, is going to be big O of N, like that. If you didn't understand where this N has come from, please just reference back to this section where I was explaining how we put in the overall function there. So I'm getting this for loop, and I'm saying C plus N plus C, and the highest order between these three is going to be N. So I've just collected that. Okay, and then the next one here as well is going to be big O of N, like that, big O of N, and then finally here we have big O of C, like so. Yes. Okay, so now that we've factored out our algorithms here and our time complexities, we are going to add this guy plus that. Let's just say this. Now, notice that this for loop is coming beneath this guy, or is nested within this first for loop. So because this one is a child of this for loop, we're going to multiply these two loops, like I mentioned earlier. And then here we're going to add this guy, like so, plus that guy. So I've got big O of the constant time plus these two, which we're going to multiply, and then we have this guy. And by rule number 1B, we say that if we have big O of C there plus, let's nest this guy, and then we say big O multiplied by N plus big O of C again there. What we're doing now is we're saying that we multiply N times N, which is going to give us big O of N squared. Yeah, that's a square there. So, okay, big O of N squared. And then when we add with this guy and with this guy here, we see that the highest order function that we have is big O of N squared. So the time complexity of this algorithm is big O of N squared. I hope that makes sense. Okay, so the same format goes here. It's just that here we have N times N. So here we have N times N. We can just try to ignore this because we know that the constant here is just big O of 1, right? So you can either put C or 1 here. It doesn't really matter. It's the same thing. So here we know that the time complexity here is 1. Actually, let me just do this. From our previous examples, we know that the time complexity here is 1, and then this guy is 1 as well. And we're not interested in the lower order terms, we're interested in the higher order terms. So from now, we're just going to ignore those, okay? So here we know that the highest order term here is n, and then here we know that the highest order term is n multiplied by n, okay? So, and remember, for nested loops, right, we multiply. So here there's a multiplication of the function there, okay? So because n times n here, this is essentially equals to n squared. So we're multiplying n squared by n. Let me just multiply that here, times n, and the time complexity big O of n cubed, right? And remember, in our rule here, let me just go back here, it says that if Tn is a polynomial of degree k, then the time complexity of that algorithm is to that, which is essentially this guy here. So I hope that makes any type of sense. I don't think, I hope it's making sense in one way or another. Yeah. So time complexity of this algorithm is that. So this one is a little bit of a homework for you. I want you to go solve it, at least for some practice and whatnot. And if there are any questions, please just message me in the group, or you can just leave a comment down below, and then I'll be able to see it and I'll reply to you as soon as possible. Thank you so much for attending, and I will see you all in the next session. Take care.